Getting that common denominator, first one was missing sine t, so we multiply by sine t times sine t. Second fraction, what's it missing in the denominator? It's missing 1 minus cosine t. So we're going to multiply top and bottom by 1 minus cosine t, yes? Now, you want to multiply or you want to write it out first? I mean, the idea here is we're going to be multiplying. You know what? Probably better. Should we go ahead and multiply it out? Let's multiply it out. Sorry, second thoughts. When we multiply, how do we multiply 1 plus cosine t and 1 minus cosine t? We're going to be FOILing, yes? 1 times 1 is 1. Outsides, 1 times minus cosine t. That's going to be a minus cosine t, right? Insides, cosine t times 1 is plus cosine t. So what do we know about minus cosine t and plus cosine t? They cancel, right? And you saw the opposite signs. You hopefully expected them to cancel. And then last, what's cosine t times minus cosine t? Minus cosine squared t. Okay. If you didn't already put it together as one fraction with the common denominator, do so now. Denominator is sine t times 1 minus cosine t. Denominators are the same. The numerators then we are just going to add. So when I add my numerators, sine squared t plus 1 minus cosine squared t. Okay. What do you see now? Pythagorean identity. And there's two different ways we can go. We talk Pythagorean identity here, but we do need to talk Pythagorean identity. How do we want to do this Pythagorean identity? Because I'm kind of curious what you guys see. One minus cosine squared t is equivalent to sine squared t. Okay, and here's what I'm going to say at this point. That's one way to go. It's not the only way to go. Now, if you're trying to go sine squared minus cosine squared, that doesn't work, does it? The sign's not right. So, and again, what was seen here was, okay, 1 minus cosine squared, that is equal to sine squared, right? So I have a sine squared t already there, plus another sine squared t now, all over sine t times 1 minus cosine t. Okay? What about the top? What's sine squared t plus sine squared t? 2 sine squared t over sine t times 1 minus cosine t. If you've made it this far and gotten stuck, this is probably where you get stuck, would be my guess. One of the thoughts you might see, but I would veto, would be canceling a sign. Because technically a sign could cancel here, but as I look forward towards my answer, what am I supposed to have? A sign in the denominator. So I don't really want that sign to cancel. I kind of want it to stay there. Just like I kind of want the 2 to stay there. What if I say we're going to go Pythagorean identity again? It's kind of taking us in a circle, but it's all right. On top, we have 2 times sine squared. What do we know about sine squared? Okay, according to Pythagorean identity, right? If sine squared plus cosine squared equals 1, then sine squared is 1 minus the cosine squared, right? Okay, hang with me. I don't think some of you believe me yet, but let's do it. So I'm going to keep 2. I'm going to change sine squared to being 1 minus cosine squared over sine times 1 minus cosine. We're almost there, believe it or not. What I need you to recognize is that 1 minus cosine squared t is similar to saying 1 minus x squared, which, okay, if you need the help, is similar to saying x squared minus 1. What am I trying to get you to do here? Factor. Because, okay, if I work backwards here, x squared minus 1, that's difference of squares, right? X and x, 1 is 1 and 1, and plus and minus. What changes if it's 1 minus x squared? Well, out front is 1 and 1. X squared is x and x, plus and minus. What form are we going with? That one right there, because ours is 1 minus cosine squared. So we're going to have the 2 out front. 1 minus cosine squared t is difference of squares. 1 breaks up into 1 times 1. What's cosine break up into? Or cosine squared? Cosine squared is cosine t times cosine t. If it multiplies to be a negative, what do we have? 1 positive, 1 negative, all over sine t times 1 minus cosine t. What happens? One minus cosine t cancels with 1 minus cosine t, and I'm left with my answer. Okay. I will say there is a spot in the middle where we could have gone a different direction. Okay, so if if you had seen something else, or if someone had helped you and you saw something else or whatever, but right here, the Pythagorean identity that was mentioned was 1 minus cosine squared t. The other option, and I'm just going to show real quick, is that instead we could have subbed out sine squared. And I had someone this morning say, wait, this isn't how I did it, and got like halfway through and was confused. But if you sub out sine squared, it can be 1 minus cosine squared t plus the 1 minus cosine squared t. And the direction you go instead here, if you sub that out instead, okay, think like terms. 1 plus 1 is 2. Minus 1 cosine squared and minus 1 cosine squared is minus 2 cosine squared. So again, my point is, if you went this way, could it have worked? Yeah. Okay. The top has a GCF of 2. If you factor out 2 there, it's 2 times 1 minus cosine squared t over the sine t times 1 minus cosine t. Well, guess what? Isn't that step right there? Okay. So, I mean, I think 39 is one. I have this one worked out 2 different ways in my notes. I have, what is it, 30? I have worked out 3 different ways in my notes. Okay, so, you know. Point is, there's multiple different pieces you could have done. You just have to make the steps be legitimate. Okay. What else should I talk about? Pick one if you need one. $33? I just looked at 33 just a brief moment ago and thought, man, morning class didn't ask about 33. I wish they would have. Because 33 is a good one. I mean, they're all good ones, but. Oh, you guys hated this one, didn't you? With the variables? I struggle to write them, you know, keep all my variables straight on this one. So, what is that? Is that lowercase alpha, I think it is? I forget. But. X sine alpha plus y sine alpha, quantity squared, plus x cosine alpha minus y sine alpha, quantity squared. I don't know if you guys have already done this one or not, but you pretty much need to allow, this is how I did it, the entire width of the paper. I don't know. It takes up space, doesn't it? And that's supposed to somehow magically become x squared plus y squared. Okay? Now, important fact, did I copy it right? Oh, I didn't copy it right. I knew something seemed wrong. Does anyone care that I didn't copy it right? Is that the only piece I didn't copy right? Yeesh. Sorry. Okay, x sine alpha, y cosine alpha. X cosine alpha minus y sine alpha, quantity squared. Okay, guys. You ready? What is step 1? Okay, it's a squared, yes. Officially, in order to square these, we technically need to FOIL. Okay. So we can't just tag squares on them, we have to FOIL. And I think I'm going to work mine under here so I have the width of my screen. So if we FOIL, do you need me to write this out? Okay, so optional line here. I don't know. Do you feel it's going to be more helpful if you write this out side by side? X sine alpha plus y cosine alpha. That's the first one we're squaring, yes? In order to square it, think FOIL. If you don't want to write them out side by side, that's fine. So what is x sine alpha times x sine alpha? Kind of like saying, what is AB times AB? So you can either write it as A squared B squared or AB quantity squared. For what we're doing, I'm going to go with the technique of A squared B squared. So what is x sine alpha times x sine alpha? X times x is x squared. Sine times sine is sine squared alpha. Outside, x sine alpha times y cosine alpha. Well, I'm going to leave a space in front of it, but realize x times y is xy. Sine times cosine is sine alpha, cosine alpha. Why did I leave a space in front of it? My insides. Y cosine alpha times x sine alpha. X times y is xy. Cosine alpha times sine alpha is another sine cosine. So what happens here? We have what? We have 2. And then lastly, y cosine alpha times y cosine alpha. Y squared cosine squared alpha. That's the first piece. And now we say plus the second piece. And again, it's not that you have to show the setup for FOIL. I just thought it was easier to teach that way. So x times cosine alpha minus y sine alpha. Okay, so x cosine alpha times x cosine alpha. X squared cosine squared. X cosine alpha times negative y sine alpha. Well, positive times negative is going to make it negative. X times y is going to make it xy. I left a gap again. Cosine times sine is going to make it cosine alpha, sine alpha. That's my outsides. What about my insides? Negative times positive, x times y, cosine times sine are all the same pieces there. So a negative 1 and a negative 1 is going to make this negative 2. And lastly, negative y sine alpha times negative y sine alpha is going to be plus y squared sine squared. Okay? What do you see happening importantly? Plus 2xy sine cosine cancels with minus 2xy sine cosine, yes? Any other like terms? There's not, is there? Okay. So, with that in mind, we have 4 terms left, yes? Rearrange these so something like about them are next to each other. We could do this one of 2 ways. I don't really care which. We can put both x squared terms out front, or we could think about putting both sine squared terms out front, or both y squared, or both cosine squared, right? But we need to rearrange these so we can have a visual of something. I'm going to go ahead and put my x squared terms out front. So I'm going to keep x squared sine squared. Plus, I'm going to pull the other x squared term, so plus x squared cosine squared. Then I'm going to put my y squareds. So y squared cosine squared plus y squared sine squared. Okay. 4 terms. I'm guessing we don't know, but do we know? There's 4 terms. The way I set it up is the first 2 have something in common, and the second 2 have something in common. So we can set this up as factoring by grouping, which is what you use within product of AC. Okay, factoring by grouping is when you have 4 terms, split them in half, GCF of the first two, and then GCF of the second two. So if I split this in half, there's my half. What's GCF of the first two? My first two terms have an x squared. So I'm going to factor out x squared, and then I'm left with sine squared alpha plus cosine squared alpha plus GCF of the second two. What do they have in common? Y squared. And then what remains is cosine squared alpha plus sine squared alpha. Okay? We can take one of two views to finish this off. Which view are you guys seeing? What? Do we see two Pythagorean identities here? Yes? So we have x squared times, what is sine squared plus cosine squared? 1. We have y squared times, what is cosine squared plus sine squared? 1. What x squared times 1 plus y squared times 1 is x squared plus y squared. What?
It's the worst thing I've ever done.
It's not the worst. As I said, I just realized morning class didn't ask about that one, so I'll be curious when I go to look at theirs how that looks.
I did not do that.
What?
What was the other way you were wanting to do it?
Well, the other way here, right here at the end, is if you finish off your factoring by grouping. So we have GCFs of x squared plus y squared. And then what's the common piece? Even though they're in different orders, they both have a sine squared alpha plus cosine squared alpha. Yes? And so then I'm just, if you finish off the factoring by grouping, you have x squared plus y squared times what? 1. I mean, it's essentially the same thing. It's just, do you see Pythagorean identities here, or do you see finish off the factor by grouping? So. Not a necessity by any means, but. Okay. What else? 24? What is 24? 1 over tangent beta plus tangent beta. And what's that supposed to equal? Secant beta, cosecant beta?
Should I just switch the betas with x's?
Sure.
Okay, sweet.
I mean, technically, ideally, should we be using the variables they give us?
Yeah.
Technically, ideally, yes. However, I don't hold it against you if you change variables, and just be consistent and don't back and forth between steps or something. Keep it the same all the way throughout the problem. Okay. Well, thoughts? We have tangents right now. We have two terms being added. We're supposed to magically get to secants and cosecants. It's going to be one term, no more adding. Okay. Common denominator? I'm trying to process through. I was going to get a common denominator, but I was going to do a different step first. So if you get a common denominator, what you end up with, okay. Sorry, I'm just trying to process if I want to go that way or not. That's my alternate way. That's what I have. Okay. Okay, so I can go common denominator. I just had to make sure it was gonna, not go horribly astray. But it actually looks like it works pretty, fairly well. When you get common, my other thought was change the sines and cosines. Okay, both work. What'd you say you did?
I got puzzled.
With which one?
After switching.
To sines and cosines? Yeah, either. At some point, you're probably going to want to switch to sines and cosines either way, too. So, let's see. Tate, you asked about this one. You start off with sines and cosines? Okay, I'm going to go that way. Again, getting a common denominator right now works as well. Okay, I do see that. So if we go sines and cosines, what is 1 over tangent? It's 1 over sine over cosine. Plus, what is tangent here? Sine over cosine. Now, before we go any farther, what is 1 divided by sine? 1 divided by sine over cosine. Cosine over sine. In other words, I'm just saying we probably should get it you don't want to hang around with all the fractions within fractions. Okay? And we could have also, I guess, 1 over tangent. What could we have turned that with to begin with, I guess? 1 over tangent is cosine, yes? Or cotangent. And is this cotangent? Yeah. So at this point, if you are here, you should get a common denominator. In other words, if you haven't added them, you've hit that point where you need to. What's my common denominator going to be? Sine times cosine gives me a common denominator of sine cosine. Sine beta, cosine beta, yes? First fraction. What is my denominator missing? It's missing what? Cosine. So I'm going to multiply top and bottom by cosine. What's cosine times cosine? Cosine squared b. Second fraction. What's my denominator missing? Has cosine, it's missing sine. I multiply my bottom by sine, I'm going to multiply my top by sine. Sine times sine is sine squared b. I didn't ask, I just did it, but I went ahead and put it together as one fraction. Okay, it says, oh, who sees it now? What is sine squared plus cosine squared? That's 1. So 1 over sine beta, cosine beta. Well, I could argue you're there and you don't even have to write another step. You see you're there. And this is where if you need the visual, break it up. Think of this as 1 over sine beta times 1 over cosine beta, right? You don't have to write that step though. I am fine with you stopping right there. But then realize that 1 over sine is cosecant, and 1 over cosine is secant. Okay? Those are kind of extra steps if you feel the need. But you could finish off right there. I mean, obviously you write the final, write the final piece. Okay. What else? What is it? 30. 30? Yep, we did this one this morning. So 30, tangent squared theta minus sine squared theta. And my job is to make those multiply, right? Yep. Tan squared theta times sine squared theta. Okay. 30. Thoughts on getting started? I know what my brain is thinking.
Once you get rid of the tangent, break it up into sine squared theta over cosine squared theta.
Change everything to sines and cosines. That's one of, this is the one I have worked 3 different ways. Yep. But I think in all of them I start off with going sine and cosines. So we know tangent squared is sine squared over cosine squared theta minus sine squared theta. I'm going to go ahead and say, what is sine squared theta as a fraction? Sine squared theta over 1. Why am I suggesting that? We're going from subtracting to having one answer, no subtracting. So we probably need to get a common denominator. What is my common denominator?
Cosine squared.
Cosine squared theta, yes? So same thing I asked earlier. What's my first fraction missing? Oh, nothing, right? Just stay sine squared theta minus, what's my second fraction missing? It's missing the cosine squared theta, so we're going to multiply top and bottom by cosine squared theta. So sine squared theta times cosine squared theta is sine squared theta cosine squared theta. Okay. What could we do in that numerator is what my brain sees. What do both terms have in common? Sine squared? If I factor out GCF on top of sine squared, sine squared theta, what remains? Sine squared divided by sine squared leaves me with 1 minus sine squared cosine squared divided by sine squared leaves me with what? Cosine squared. All over cosine squared. As I said, I just want to work 3 different ways in my notes. So often, if I see other ways that I see you guys work, I add them to my notes. So what do you see? Do we see a Pythagorean theorem? Okay. A Pythagorean identity? I'm going to leave sine squared. What is 1 minus cosine squared according to our Pythagorean identities? It's sine squared, yes? All over cosine squared. Have you checked to see what we're going towards lately? We want tangent times sine. Excuse me, tangent squared times sine squared. Do you see it? We're there, yes? Because right here, don't go multiplying sine to the fourth. That takes you too far. If your brain, the visual is, okay, we have a sine squared theta over cosine squared theta times, we also have a sine squared theta over 1. Those multiply back together to be what we had previously. But then down below, sine squared over cosine squared is tangent squared. Sine squared over 1 is sine squared. Okay? And again, if I've gone one way and you're like, man, I had this other way that worked perfectly fine, I'm not going to say it's wrong until I check it. Okay? I'll always check against my worked out answers, and then if you diverge, then I'll follow you until you make a mistake. Then I'll mark it wrong. But if I can follow every step, then it's good. Okay? Got some good answers? Okay. Hopefully you got most or all of your questions answered.